So this is a pretty easy program to make. We're going to do my-md5. And then inside of there, I'm going to make a new file. Main.go. And we're just going to copy over that function, that program. Except instead of fnv, we're going to use md5.new. And that's in crypto, which it does for me, crypto md5. I'm going to do the same IO copy, except in this case we're going to use printf and say %x. And then instead of sum, it's sum nil. Okay? And the way we found all that out is we went to godoc.org/crypto md5, and we went and saw this example, and it does pretty much exactly what we were doing. I think those are quotes from Airplane. You guys remember Airplane? Yeah. Anyway, so we go to my-md5, go install. Cool, that worked. And then we type my-md5. And that computes the MD5 of a file, so we give it a file name. I'm just going to give it itself, and there we go. So maybe we'll add a new one to that.
The %x again, that's just saying the %x.
It formats it as hexadecimal. So if you looked up the documentation in format, it would tell you that. You can also use the hex library to do this, hex.encode to string. But this is way easier. So notice this number. I mean, it had all this extra stuff inside of it. It changed dramatically. Okay, even though I only changed like 1 byte of the file, the number is completely different. And that's how MD5s are supposed to work. Does everybody understand this idea of hashing? What we're doing here? So maybe a way to think about hashing is. If we had a number and we broke it down to binary, so we had like 1, 2, 3, 4, and so we had all these numbers, and we wanted to compute a 1-bit hash. One way we could do that is just look at this last, we could like add them all up, right? And so if the number of ones was even, we'd say 0, and if the number of ones was odd, we'd say 1, right? And so this is a 1-bit hash. Okay, now this hash isn't very good because there's only 2 possible values for it. So half of the numbers collide with each other, right? Half of the numbers have the exact same, like these 2 numbers, even though they're different, they have the same hash. Okay, this is called a pairing bit, and it's used all over computers, but it's the same idea. They use that hashing bit as an easy way to check a parity bit, to check that something changed. Okay, like if you know this number changed, something went wrong because a bit got flipped somewhere. Anyway, so we use hashes a lot. I mean, I don't know how much you might know, but sometimes we have to use them. We saw it the other day with the Gravatar thing; it required a hash. So you will often see MD5. In general, for new code, you should not be using MD5. It's no longer secure. The other one we see a lot of is SHA-1, SHA-1. SHA-1 is also considered not secure. The thing about SHA-1 is this is used by Git, Git, to store everything inside of your repository. It uses a SHA-1. Okay, so it doesn't use the names you give things, it uses the SHA-1 of their contents. And if you give a file with exactly the same contents, you'll have the same. You should be using maybe SHA-256. And that's still secure until they discover some vulnerability in it. And we move on to something else, but so yeah, we do use hashes sometimes. And like I said, it's useful if you have some huge thing of data and you want a number. So if you want to compare 2 huge things of data, it's a good handy thing to be able to do. Okay, so I'll walk through the next example.
So you said SHA-1's no good, SHA-256 is still fine. There's one before that.
MD5.
MD5
the one we use.
No good anymore.
No good. Deprecated. Obsolete.
And FNV, is that a newer one? That's good?
FNV is not cryptographic. So it does not have that property of, you can guess it from an FNB, the file name, very easily. So why this difference? Well, the reason FNB is very, very fast. It's super fast, whereas SHA-1s are slower. But the truth is SHA-1s are also very, very fast. Like Intel, with their newer processors, added instructions to the actual processor to calculate the SHA-1. So they actually do it in hardware now. You don't even have software to do it. They did that because it's so common. SHA-1s are everywhere. They're used for so much stuff. They were like, well, we'll put it in the CPU to make it faster. So, along with other things.
So, like if you're going to store user passwords, do you use SHA-1 or 256? SHA-1's not secure, so 256?
Yeah, so that's one way to do it. So this idea of user passwords, you probably don't want to store passwords inside the database, because if you get hacked and they get access to your database, they see the passwords of everybody's account. And because we're people, we use the same passwords everywhere. So now that person might have access to somebody's account somewhere else. So to minimize the risk of your hack causing damage to other places, to sort of minimize the collateral damage of that, we can hash the password and store that. And then when they try to log in, we hash the password they entered again and compare those two. And so if the hashes are the same, we know they entered the same password, but we don't know the password that made the hash, okay? And that's why that cryptographic property is important, because I don't want to be able to figure out what the password was. So, though instead of just doing that, we should use something called vcrypt or scrypt, which work very similarly, but they basically run the SHA lots and lots and lots and lots of times. And the reason they do that is because then it slows it way down to make it so you can't do it very often, which makes it harder to guess. But anyway, so scrypt or vcrypt if you want to store passwords in a database. It's kind of funny because that's an example of we made the hashing so fast that now we have to slow it down in order to make it secure. Okay, so the next example is to turn this and make it do more than one file, to do a whole directory, okay? So let's look at that problem. Modify number 2 so that it computes all the MD5 checksums for a directory. Okay, so
just as a question for everybody, what method do you think you'd like go to Google and search for Golang space what?
what's the directory?
Yeah, like read a directory or dir or something.
Right, we might say list directory. We'd see this, and we might think, oh, I should use redir. You could do that. You're better off using this. Walk. Walk's a directory. Okay. Walk walks the file tree of root calling walk function for each file or directory in the tree, including root. All errors that arise visiting files and directories are filtered. Tells you a bunch of other details. It's pretty easy to use, and as far as how would you know to use this instead of that, I have no idea. You just have to know that.
And redir is not recursive and walk is?
That's right. Yep.
So walk will go down into subfolders, but redir won't.
That's right. So this will no longer take an argument, and we're going to basically, we need to walk. So we use file path dot walk. You give it a directory. I'm going to give it dot, which means the current directory. Everybody following that? And then you give it a function. Okay? Now here's something interesting. Here's the second argument, walk func. So it says walk func is a function that takes three things. It takes the path, info, and error, and then it might return an error. So we have to match this definition. So I'm going to copy that and paste it in here. Okay. Remember callbacks from JavaScript? This should look familiar. This is a callback to go. Okay, so I'm passing a function to the walk function. And it will invoke this function for every file inside of it. Okay? And not just files, but folders. And so the first file it starts with is the current folder. So it's going to go to this folder, and that's the first time it'll call it. And then it'll list all the files inside of it, and it will call this function for every one of those. And then if there are folders, it'll go into those folders and list them, and so on, recursively. So just to see what it does, let's just print line info. Let me comment all this out. We're going to need it in a second.
So you don't need to pass anything into the func there? Those are passed in automatically by walk?
Yeah, walk is going to fill these in.
Okay.
We have to return something, it returns an error. If we returned an error, it would stop walking. So we're just going to return nil, so it walks the whole thing. Okay, does it make sense? If I return an error in this function, it immediately stops walking. Because if I was walking this huge tree and I'm like, I only want to see the first 5 files, then I can stop it. Okay? Or if there was an error, I could do that. So this should print all of the directory contents of the current directories. So go install. It's the same program, MyMD5. So it would return 2, okay? And like I said, the reason it returns 2 is it returns the current folder and then all the files in the folder. There's only one file in this folder, main.go. So it only has that. These other things are details about the file. It's length, it's modification, pointers, all kinds of stuff. And we can get that info from the docs, right? So it says it's a file info. And we could see name, size, mode, time, isdir. So the first thing we're going to want to do here is we are only interested in finding the MD5 checksum of files. So we'll say if info.isdir return nil. So we're skipping directories basically. Okay? So now we should only see main.go. I skipped the directory. I don't care about that. I'm not checksumming a directory. I'm checksumming the files of the directory. So to make this more interesting, let's make a directory test and then fill it with a file, test/hi.txt, okay? And now I'm going to rerun that program. Did I put that in the right place? Should have filled it in. Let me, it's possible there was an error. That's odd. Maybe I didn't, it says there's nothing in text. Didn't I write a file? Oh, apparently I didn't. Okay. That's why it didn't work. There we go. So now we have 2 files. One's inside of that test folder, and one's right here in the root folder. So I don't need this one. And so we just need to call this bit of code for each file. And so what I'm going to do is make a function called MD5. Well, I'm not going to call it MD5. I'm going to call it MD5 file. You give it the file name, and it returns the checksum of that file. And so we're just going to copy and paste that code we wrote. And instead of printing it, we're going to return h.sum. And so now we can just call this function to do that, which makes this bit of code a lot easier. Because now I just have to say, give it the file name, which I can either use path, or I can use info.name. I'm going to use path because it's right there. And that gives me back the bytes. Okay? And so if I print this, what's this going to do?
Print byte size?
Yeah. How many times are we going to see that?
2.
2, exactly. 2 because there's 2 files. Oh no, what did I do wrong?
Index out range.
Ah. copy and paste code. It was looking for arguments of it manually. There we go. So, 2 files results in 2 slices of bytes. We just format them with printf, like we did before, with %x, and then our bytes, and we'll rerun it. And now we're getting the checksums, but they're all combined together, so we should add a new line. And I think to match, I think we should put the name of the file in there too. If I have an example here. But we'll see that later. But basically, you put the name of the file here, so we can say that with %s, and then path. Okay? So now it has the name of the file, space, and the checksum of the file. Okay? Make sense? Pretty straightforward.
Copy that code from scratch, please.
So that's how you walk a directory. Just there's an example in there, and you can use this code as a sample. It's pretty easy. This is very much like Python, which also has a walk function, and it's a very similar idea. Just recognizes recursive. And this is how you visit every file. Okay, pretty straightforward. But as far as this is very much the same. Right? We could make a function. Ways we can improve this. For one, you know, these errors, we shouldn't just be panicking. We should probably return them. We're just going to panic. If I couldn't read the file, for example, die. Okay. Okay, we'll get started on this. We're not going to finish this before lunch, but we'll get started. Maybe that's better anyway. So one downside of this program is it does 1 file at a time. And our computers have multiple cores, lots of RAM, lots of resources available to them. So when we run a program like this, it only uses 1 core of our machine. Okay? And pretty much everybody's laptop here has probably at least 4 cores, if not more. And servers often have, say, 64 cores or some huge number. And so we're not using all of the CPU we have available. We're only using 1. So it would be nice if instead of doing these 1 at a time, we could do all the files at once. That's the idea. Okay? So I'd want to be able to do, I'd be MD5ing the first one and the second one at the same time. That would be nice. Then I could maybe use 2 cores of my CPU. And the way we do that is by using concurrency. Okay? So.
Because traditionally the way that code runs is just, you know, it goes through loop, it does 1 at a time, the next one, the next one. It's just running sequentially or serially, right? One after the other.
Yeah. So large programs are often made with smaller subprograms. A web server handles requests. In our example, this MD5 file bit, you can think of as a subprogram, right? Because we transformed this program into one that worked on multiple directory files. So it'd be ideal for programs like these to be able to run their smaller components at the same time. So you're making more than 1 progress on a task simultaneously is known as concurrency. I'm doing 2 things at once. The important thing here is you're not necessarily actually doing them at the same time. So if we imagine I have a process P, and it runs like this, and then I have a process, call that P1 and P2, and it also runs like this. There's sort of 2 ways we can run this. We can run them right after each other. So I have P1 and then P2, right? I could run them simultaneously like this. I can also run them like this. Do P1, part of P1, and then part of P2, and then go back to P1 and do some of that, and then go back to P2, and so on, okay? And so the point is concurrency can mean this, it can also mean this. It means making progress on multiple things. But how do you make that progress is not as important. It just means that we're not having to wait for the first one to finish before we make progress on the second one. We're making progress on both. There's this time slicing approach. When back when CPUs only had 1 core, this is how they did multiple programs. Okay? Right? You would like do a little bit of Excel and then swap to your browser, do a little bit of that, and then sometimes that swapping back and forth was really costly, and so your computer just sat there and did nothing for a while. And so that's what is happening. Computers still do this. I mean, they're still doing this time slicing stuff. But we now have the ability to actually run two things at once. So the way you can think of a task is just like a task you normally do. Like, say you're like watching a TV show and working on a chore, like folding laundry at the same time. Or maybe you're folding laundry and cooking dinner, okay? Right? You could fold all the laundry and then go cook dinner. Or, like I often have to do when I do laundry, I go put it in the machine, and then I start cooking dinner, and then when it's ready, I go to the machine and take it out, and start folding it, and then I wait for dinner to finish. You know, you're making progress on both tasks simultaneously, right? And so instead of taking 2 hours, it only takes 1 hour, because there's a lot of waiting in between the two. Okay? Everybody following the idea of a concurrency?
Good example.
Yeah. So, concurrency is great to add to a program. In most languages, concurrency is very difficult to add. And the reason why is we're often using the same resources, okay? Like, we're both trying to access the same thing at the same time. And we can't do that, otherwise bad things happen. So coordinating the two can be hard, the two tasks, unless they're really completely independent. And then that's easy, but if they're not, then it's difficult. So the way we do concurrency is with Go routines and channels. So a Go routine, which sounds like a coroutine, which is a concept from computers, is like a thread, if you're familiar with threads in other programming languages. So a Go routine is a function that is capable of running concurrently with other functions. To create a Go routine, we use the keyword Go. So this is why Go is named Go, for one of the reasons. It's Go, and we give it a function name, and we call it. So let's look at this code. We'll run it. I'll make a new folder. I'll call it concurrent example. And we'll add a main Go. And we'll run it. Okay. So what this does is it prints 0 and then all these numbers. And then it's scanning, so it's just waiting for it to hit enter. So what this did was, it called main and it called F0. And what this did is it started another concurrent task, F. And then immediately it went to the next line, okay? So this is happening somewhere else. And then we come right back to here and start running. So we don't wait for this to finish. This whole thing doesn't finish before we go to this line. It actually goes and runs. Normally when you run a function, the function has to complete before you go to the next line. But with Go, it's as if it's like, put this in the background and start running, okay? If you use the shell, it's like the ampersand at the end of the shell, which means run a task in the background. It's that same idea. And so that's what Go is doing. So remember how I talked about a stack? And we had that stack and the heap and all that? Yeah. We had, you know, stack up here, heap up down here. It turns out we actually have multiple stacks, one for each Go routine. So think of the stack as, right, they each have their own, and this is process 1, process 2, process 3. Down here we have a shared heap, and they all have access to the same heap, but they only have access to their stack. Okay. So when we say Go F0, it's like, go start a new one, give it a new stack, and start running, okay? And these are running, like I said, they could be simultaneously, they could be time slicing.
Does that mean you can actually time them?
Time? You mean like?
You can say, for instance, run this function, and then I don't know how many milliseconds the second one will start, or something like that.
Yeah, so we'll see time a little bit later, but we can do things like sleep. So we can put this guy to sleep for a few seconds and then start it. We can do all kinds of stuff. And we can also coordinate them with channels, which we'll also see in a second. And so, but the basic idea, everybody following the basic idea of doing more than one thing at a time, these are the multiple tasks. This is how I start a task. Okay. So the thing to remember, keep in mind here, main itself is one Go routine. So every Go program is running at least one Go routine all the time. It's as if what Go, the compiler says, it says Go main as the very first thing, okay? And now we have our first go routine, and then this guy starts off another go routine that goes and runs at 0. Okay? So go routines are always like this. They're always a function invocation. They're always calling a function. They can take arguments like 0 here, but it's a function call. So we can make as many of these as we want. You know, you can make 100 of these, 1,000 of these. I'll show you that. Let me see if there's an example in the book again. I don't remember. Yeah, so here we go. So I'm going to change the main here. So all it's doing is printing 1 to 10. That's all it's doing. I'm going to change it so that it fires off 10 of those, okay? So, yeah, this is right. So it loops 10 times and prints out I and then n. N is whatever you passed in. So that's why we saw 0:1, 0:2. We saw that because of the n. So this time we're going to set it to this. So now we should expect something like 0:0, that 10 times, and then 1:0, 1:1, 1:2, and so on. So we should have 100 prints is what I'm saying. Okay. So this is starting 10 tasks concurrently with this program.
And if there wasn't concurrency, we would see 0, 1, 0, 2, 0, 3, then 1, 1, 1, 2, then all the way sequentially, right?
We may still see that,
If there wasn't concurrency.
even with concurrency.
You're going to print them as they finish or print them in the order that you want them to be.
Okay, so this is what happened. It started task 0. This is the task. In fact, let me just add that to so it's more clear. And we'll put, we'll call this the number. Or step, let's call it step. Okay. Yeah. Okay. So here's what happened. It did task 0, step 0, and then it decided to run task 1, step 0. Notice that all the task 0, the rest of them are down here. Okay. So the order here, it's running them all simultaneously, so the order can be all mixed up, right? Because we're printing to the same terminal. We're all printing the same terminal, but there's 10 of them printing, okay? They're all trying to print at the same time, and it sort of interleaves them however it sees fit. And like I said, it's making progress on multiple tasks at the same time, and so it doesn't necessarily mean that they literally all write at the same time. It just means they're all moving along the way. Okay, question?
Yeah, so if it's running multiple functions, but say you might be getting to this, one of the functions requires something of another function to continue its operation.
Yeah. Yeah, so
So in other words, it's going to write, will it first calculate that out and then start the whole looping of concurrent functions then?
that's something we have to define. The relationship between the go routines is up to us. And so we'll see how we communicate between them. But yeah, the ordering is unpredictable because there are multiple things happening at the same time. And this is actually what makes concurrent programming very difficult to reason about, is it works right once, but maybe the second time it doesn't, right? Because the ordering of how things happen is kind of random. It's hard to predict. And so there are whole classes of bugs. They call them Heisenberg bugs that you try to look at it and then it goes away, like like a Heisenberg. And so the whole classes of bugs having to do with concurrent programs, where it works 99.9% of the time, but that 0.1% of the time it breaks, and it's so hard to reproduce. And so Go gives us things that make that easier, so we can be sure it's correct. Okay. So there's a little graphic. Let's see if I can find it. That I think illustrates this idea of the. There we go. Everybody see that? The gophers. Okay. So imagine this guy. He's trying to burn books. He's burning books. So he has books over here, and he's putting them in the middle, and then this other gopher is burning them. Okay. And so the idea is that these are two separate Go routines. This is one Go routine, and that's another Go routine. Okay. So they're running at the same time. See, they're running at the same time. But they have a bit in the middle that is coordinating the communication between the two.
But it is a sequential process. Because the second gopher can't operate until the first gopher is done with his process. So the entire
yes.
process is sequential, as I see it. The two individual functions are operating simultaneously, but
You're right.
the first time it goes through, only one function is functioning.
That's right.
Right.
So think of it like this. I have P1 and P2, right? And this is going, and now that this has happened, he's dropped the first book off,
Yeah.
P2 can start, okay? Now, and normally, if it were completely sequential, P2 would run and then P1 would start. But because this is using a separate task, P1 starts immediately. He runs back, goes to the next book, and then goes, right? And so actually it works like this. You follow it? So we're actually going twice as fast as we would be otherwise.
Well, isn't that based on the fact that the first gopher is not waiting for the second gopher to complete its task?
That's right, exactly. And that's the advantage of concurrency. We've just made a program that's twice as fast as it was before by adding a go routine. Okay.
But yeah, each one has to wait. They can only be one.
But he doesn't do it more than twice without waiting. Yeah. What's the reason for that?
Yeah, because he has to place on an empty space and the other guy has to take from a full space.
That guy's like waiting. There's only two empty spaces. Look, you see right
You
here.
can watch this all day. It's a random amount of time how fast it goes. So.
What's the quote that says concurrency is not parallelism? Is that exactly what you just drew? That they're not going at the same time?
So this is a talk that Rob Pike gave, and it's definitely worth watching, and maybe we will at the end of the day or something. And it's it talks about some patterns and things that are really good for concurrency. But that's the point I was making about, it doesn't necessarily mean the two tasks are happening simultaneously. It just means that progress is happening at the same time. Parallelism means they happen simultaneously.
So they're both working, but it doesn't mean that they're working, doing the same thing.
Right. Yeah. So anyway, I just like that picture of the gophers. Okay, so it says you may have noticed that when you run this program, it seems to run Go in this order. We saw that it kind of did. I think earlier versions of Go it was more in order. Now it's a little less predictable.
Mine was all zeros on the left, like at the start, and then
Yeah.
I ran it like 6 times and nothing changed.
Yep. And so we can add some delay just to make it look more realistic. Like normally, this is not the kind of program you'd add concurrency to because it doesn't buy you much. But most concurrent programs, they involve doing things like reading files and stuff that takes different amounts of time. So let's do this. And what we're doing is we're going to sleep for a random amount of time. Okay. We'll talk about time later, but this is just going to make it wait a little while before it prints the next one. And so let's run this program instead. Okay, so it's doing the same thing. We're still printing, but this time we're just going to wait a little while before printing the next one.
Where did you get that?
I got them all there on top of that.
There we go. See now how they're all mixed up?
Yeah.
And that's because they all took a random amount of time to sleep. And it prints as soon as it can, it does the next operation. So we get them all mixed up, right? So the basic idea is if I have 10 of these tasks running, and they each take 2 seconds, the whole thing takes about 2 seconds. It doesn't take 20 seconds. Because I'm doing them all at the same time, okay? And we can actually see that if I take out the go here. So I'll run this again. That took about a second or something. And then I'll reinstall, and then I'll run it again. Significantly longer, right? Because now it's doing them in order. It's waiting for them to finish. So we're just going to kill it. And all I changed was go. I made go F called it without.
Where you switch out and go.
Yeah, before to make it slower. So keep in mind this does 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? This is running in its own go routine, its main function. So it calls off all 10. It's not waiting for these to do anything. It just just immediately goes to the next one, and then it waits down here for me to enter something, okay? So if we look at the program, I can just immediately exit, okay? So what it's doing, the scan line is waiting for me to enter something, right? As soon as I enter something, it exits the program. So the thing to remember here is when main finishes, all the other go routines stop too, even if they're not finished yet, okay? So main just finishes the program, and all the other go routines die. So usually when you're working with go routines, you have to do something here to make it wait. And there's different ways you can do that, but that's the basic idea.
So,
The main go routine has to stay alive. Yeah?
so if you say you had to print something at the very end instead of a scan, it would just immediately go through it would start all the programs and then just print what you wanted to print and it'd be done.
Okay, so what do we think this is going to do?
Well, if you take out the scan, it won't wait for you.
No, it will not wait. The program will just finish
And
it.
the program will finish.
But what do we think this will do?
After it starts all 10, it will print hello world and then wait for you to.
Yeah. So where do you think Hello World will be? Do you think it'll be at the top? Do you think it'll be in the middle somewhere? Do you think it'll be at the bottom?
I think it'll be random.
Random?
Top,
Bottom?
top.
Top? Okay.
Top-ish.
Yeah, I like that. Top-ish.
Yeah, very
Yeah.
top.
Truthy.
Top-ish. Right? It's at the top. Why does that happen? Right? Because it does all these go routines. It doesn't wait for them to go do anything. It just immediately goes to the next one, and then it actually, you know, your computer can move over 10 things very, very, very quickly. So this happens immediately, basically. Right? That's it.
But it's possible that if you took out the wait time on the function F, that hello world would actually.
It is possible, absolutely. And in fact, even in the current form, it's possible for Hello World not to be at the top.
That's why I said top-ish. It could be one or two below, because the first couple go routines usually get their print lines first.
I read somewhere that it takes a moment for go routine to sort of fire up.
Yeah, because you've got to build that stack and some other stuff, and so it does take a bit to get it going.
Why does it do that?
Well, so it has to build that stack of memory and stuff.
The heap in the middle where they're stacking up the info.
Remember we had that diagram with the stack and there were 3 of them?
Right, yeah.
So Go, like the runtime has to go set those up for you before it starts actually executing code. And so that takes a little bit of time. Not as much as a thread, okay? So if you're familiar with threads are kind of expensive, they're pricey. Go routines are very lightweight. So on a normal computer, you can have thousands of threads, maybe 10,000. Go routines, you could have millions, that's okay. Okay? So Go routines are very lightweight threads. You can think of them like that. So don't be afraid to say Go whatever. Okay? Yeah, it's expensive, but it's not that expensive. It's pretty lightweight. Is everybody following this?
Yeah.
Okay. I'm going to go through channels, and then after lunch, I'll go through channels all over again. Okay? Because we have 10 minutes, and that's probably not enough time. So channels provide a way for 2 Go routines to communicate with one another and synchronize their execution. So here is an example program using channels. So this is pinger and printer, and what it does is it sends ping on a channel, and then this guy's reading that channel and printing it out. So the channel here is a type. So this is a channel of strings. So think of channel like, channel is a good name for it. It's something you send data over. Okay? It's like a pipe or something like that. Okay? So I have task 1, right? And task 2. They're running along, you know, and at some point I want to send data to a different task. At some point I want Go for 1 to communicate with Go for 2. And so I use a channel. So if we imagine that there's this channel between the two, and I send data to that channel. Now task 2, this is just going to sit here, okay, and wait. It's going to, like sweep kind of, it's just going to wait until somebody is on the other end of the channel to receive. So imagine task 2 comes running down until we get to here, right? So actually the channel ends up, you know, it like does this number. and then he receives from the channel. So they're synchronized. At this point, the two are synchronized together. So we know that this line runs at the same time as this line. Okay? Because this one's waiting until something is pulling off of it. So it's not like I put it in here and then it's sitting there and I go on my merry way. It's I put it in here and wait till somebody's ready to pull off. It's as if you're having a conversation with a person, right? You don't just like throw your words out there and then they come by an hour later and they get them. They have to be there. You have to talk to them. Okay. So that's what we're doing with the synchronization between. And we use a channel. So this is a channel of strings. That's the type of things we send over the channel. So I'm sending a string. You can send an integer. You can send a number. You can send anything you want. You can send structs that we've seen. And so pinger is going to write to this channel. That's this arrow operator. So left angle bracket dash. Okay. And read that like I'm sending ping to the channel. And then printer, who's printing ping, so he's taking those pings and printing them to the screen. He is receiving from the channel. So send to the channel, receive from the channel. So it's the same arrow, just the other direction, right? So C goes this way, this goes this way as well, right? But in this case, I'm sending to the channel, right? And imagine this channel is coming over here, and it goes right here, right? Get the idea here. And I'm pulling it back out. Okay? It's like at the bank, you know, you have the little pipe thing you put stuff in, and it goes to the bank teller. We're doing sending ping through the thing, and it comes out here. So that's message. So this message is ping. Right? Sent over the channel. So that's how we communicate between go routines, is by a channel. Everybody follow? So this is the type, GN string. These are two operators, like plus and minus and division. This is another kind of operator. Okay. So this is the left side, this is the right side. In the middle we have the arrow. This is just on the left, just one. It's like a minus or a exclamation point, a unary operator. Okay. And it takes a channel and it returns whatever the type of channel is. So see here, when I receive from it, returns a string. And see here, when I send to it, this has to be a string. Okay. Yeah?
C just a name, right?
Yeah, we can call it anything we want.
Could C be different in the two functions? Different from each other?
Yep, absolutely, because these are functions, so the names, they don't have to match, they can refer to the same thing. So channels are passed by, they're like pointers. Okay? They're not copied, like if I pass in a channel, because there's no reason why you'd ever want to copy a channel like that. Like, they always refer to the same channel. So if I send to it, it's going to the same function. So if you look down at the main function, I make the channel here. C channel string equal make, and I make it. So this is just like making the slice or the map. Same exact syntax, we just use chan string. And then I'm passing it to the two functions. So this is the same channel, right? This channel is the same as this one. Not because they have the same name, but because I passed it to the function. Okay? So these are all the same. So the way what this does is pinger starts running, and he sends ping to the channel over and over again. And then we start printer, and he starts running, and what he does is he pulls messages out of the channel, receives from them, and then he prints them. And then he waits a little while, and then he prints them. Okay? Everybody follow?
And why does he wait? Why is he having to wait?
Oh, because I put us asleep.
If
I
you
made
didn't
it.
put us sleep, it'd just be like,
Yeah.
It would just ping your computer consistently.
Right.
Yeah, that would be. So let's see what this code does. It should print ping endlessly, is what it should do.
Until you put it in.
Theoretically. Okay, let's run this code. It just prints ping endlessly. Okay. So 1 second between each one, because I'm saying 1 second here. 1 times a second. And I'm just printing out the message. So the way this works is, you want to think of the execution of it. I start the pinger, I start the printer, and then I'm waiting for somebody to hit enter. The pinger, it goes to here and it tries to send on the channel. Okay? And so it's waiting until printer starts and gets here. As soon as it gets here, this happens and this happens at the same time. Message is assigned to ping. It then prints ping. At the same time, while that's happening, this guy runs up to the top again and he tries to send off the channel. Okay? So while that's happening, he's printing the message, then he sleeps. Because nobody's pulling from the channel yet, this guy's sleeping, but then this guy is also waiting. He's waiting for a printer to show up in the channel to receive.
It's basically like the two gophers.
That's right. It's exactly like the two gophers. This gopher's just sitting there with the book ready. You know, he's like, "You're taking forever. Come on, I'm trying to do my job." And so
only one message can be put on the channel at a time.
Yeah, that's right. Basically, that's right.
But is the limiting, is the bottleneck because of a lack of receivers as opposed to a lack of givers as far as data transfer?
It could be either side. So I think this is good for now. Like I said, I'll repeat what I just said after lunch, and I'll explain how we can do more.
Because I remember somewhere in my math class that the fastest way to get a line of customers through is not to have multiple lines with multiple receivers and those registers. It's to have multiple registers and have one line of customers. And the first customer goes to all the available receivers. Because one customer has the option to hit 10 registers
Gotcha.
as opposed to 10 lines with 10 registers.
So what you're saying is one channel, lots of printers, lots of pingers, but only one channel, as opposed to lots of channels, each with one printer.
Exactly.
And I think you're probably right, and we'll see how to do that after.
Okay.
Okay.
Yay!
Well, no, but